Welcome back to Cypress Academy. This is PSoC 6 101. In this video, I'm going to show you how to use some of the analog features of the PSoC 6. Specifically, the SAR ADC, the voltage reference, and the OpAmp, which for some strange reason we call the CTM, or sometimes the CTB in our documentation. To use the analog resources, we really need an analog signal for an input to the PSoC 6. Conveniently enough, on the CY8C Kit 028 EPD E-Ink shield that came with your CY8C Kit 062 BLE, there is a thermistor, which is perfect for taking analog measurements. We'll use that, so let's get started. Create a new project. I'll call it 26 ADC. For this project, I want to read the voltages of the thermistor circuit using the ADC and then convert those readings into a temperature and finally print all of the data onto a terminal connected to the UART. If you haven't used a thermistor before, it's a temperature dependent variable resistor. In other words, if you know the current through it, then you can calculate the temperature with a crazy nasty formula. More on that in a minute. In order to use a thermistor, if you put it in series with another precision resistor, one that doesn't change very much with temperature, typically 0.1%. All right, let me show you a picture from the E-Ink shield schematic. You can see that the thermistor is connected to A0 and A1, and the reference resistor is connected to A2 and A3, and the intermediate node in the resistor stack between them is shorted. Typically, the best way to do a thermistor measurement is ratiometric, meaning the absolute value of the voltages aren't important. Rather, only the ratio of the voltages matters. This is how you get rid of common mode noise and offset in the measurement. The SAR ADC in the PSoC 6 can be configured to do differential measurements, which enable these ratiometric calculations. Let's get to the schematic. First, drop the UART onto the schematic. Remember, we're just going to be printing out the values of our calculations. Next, you should drop the ADC and 4 analog pins. Now I'm going to show you something new. In all of the examples that I've shown you so far, you've added components to your project. All of these components have been inside of the PSoC. Well, just like putting a comment in your C program, the PSoC creator team gave you a similar ability in the schematic. You can add off-chip components. Sometimes we call them annotation components to your schematic. These components don't actually do anything to your PSoC creator project, but they help you understand what's in your system and what your schematic outside of the PSoC looks like. These components and associated wires, they're always blue. And let me say it again, they don't do anything to your PSoC creator project. They are just there for documentation. Let's add annotation components for the thermistor and a reference resistor to our schematic so you can see what's going on. First, click on the Off-Chip tab in the component catalog. You find a bunch of different annotation components which you can use for your documentation. Let's drag and drop a resistor and a thermistor. Notice how they're blue. Remember, the blue wires and the blue components are for documentation only. Now edit the resistor and change the value to 10K and turn off the instance name. Next, edit the thermistor. Set it to 10K and turn off its instance name. Now let's look at the schematic again. Notice that there's no power source for the resistor stack. So how does that work? Well, we're going to power the stack from the PSoC by driving a logic high onto the A0 pin. All right, Alan, you mean to say that the pins can be both an analog input and a digital output at the same time? Yep, sure enough. Let me show you. Edit the first pin and change the name to A0. Turn on the external connection, turn on the digital output, and set it to high. What this does is makes it so that this pin is both a digital output as well as an analog input. so I can drive a 1 or 3.3 volts onto it. But at the same time, it can also be an analog input, which can be routed to the differential input on the SAR. How cool is that? The other new thing is that by turning on the external connection, it will give you a terminal to hook the annotation components to. Now remember, from the schematic, there was not a ground on the stack. Well, we'll use the PSoC to connect a ground, also known as a logic 0. How do we do that? The same way we did on the high side. So edit the pin and change the name to A3. Turn on the external connection and turn on the digital output and set the initial state to low. The other two pins are normal analog pins, but let's change their names to A1 and A2 and turn on the external connections. Now let's wire it all up. Notice that while I'm doing this, the wires that I connect to the external pins are blue. Remember that they don't do anything in the project. They're just there for documentation. The next thing that I want to do is configure the ADC. Notice that it was already set up for 2-channel differential measurements. First, I'll double-click on it. Now, with the default settings, the ADC can only do differential measurements from minus VREF to plus VREF, and that's only plus or minus 1.2 volts. But we know we need to measure higher voltages than that. So first, change the VREF to VDDA to increase the range. When I do this, I'm able to measure plus or minus 3.3 volts. That'll work. Next, I want to turn on averaging. Then select 256 samples. Averaging is effectively putting on a big low-pass filter, which gets rid of noise. Notice that it will be slowing down the speed of the SAR because it has to take all of those samples. Now that the schematic is done, I'll assign the pins, the UART, RX, and TX to P50 and 51, A0 to P100, A1 to P101, A2 to P102, and A3 to P103. I want to use printf, so I'll change the build settings to include standard I/O retargeting. Now, run generate application. I told you earlier that the actual temperature value of a thermistor is calculated with a big gnarly equation. Well, in PSoC 4, we have a thermistor calculator library, but I noticed that the library isn't in PSoC 6. Well, at least for now. You hear that, Misha? Let's get the thermistor library. So how do we get it in there? Well, let's make a PSoC 4 project. Do File New, Project, PSoC 4. Let's see here. I'll call it P4 Therm. Now I'll add the thermistor to the project. Now run generate application, and after a few seconds, you'll see a directory called Thermistor in the generated source. That's exactly what we need. I'll copy thermistor.h and paste it into my CM4 header files folder. And then I'll copy thermistor.c and paste it into my CM4 source files folder. Now I'll make the 2.6 ADC project the active project again, so that I don't accidentally hose myself and program the wrong thing. Then I'll make one small change to thermistor.h. Specifically, I'll delete these two includes and just include project.h. Next, I'll change the standard IO user.h to include project.h and use UART_1_HW. Finally, I'll edit some firmware. I'll open up the main_CM4 and include standard IO and thermistor.h. Then in the main function, I need to start the UART, start the ADC, and tell the ADC to start running continuously. In the main loop, I need to declare a couple of floats to be the voltage of the two differential inputs, and I need counts for the integer values that come back from the SAR. Then I read ADC channel 0 and assign it to the count reference. Remember, channel 0 is the reference resistor. Then do the same thing for the thermistor on channel 1. Next, I'll convert the counts from the 2 channels into volts. This isn't needed, but I do it just so I can print out the voltages. I'll call the thermistor library function to find out the resistance of the thermistor. This is part of what I copied over from the PSoC 4 project. Then I'll convert that value into a temperature by calling another library function. Again, copied from the PSoC 4 project. This function actually returns the temperature in hundredths of a degree Celsius, and I'd really like to have it in degrees Celsius, so I'll divide by 100. Finally, I'll print out the whole mess onto the screen, do a delay, and then loop back to the start. Now, for the moment of truth, hit program. When I open up the terminal, I can see that 5 times a second I'm seeing the voltages and the temperature. How cool is that? Now when I put my finger on the thermistor, it warms up, and yes, I can see new values. Next, I'll take my fluke meter with a thermocouple, and looky there, the fluke says nearly the same thing as the PSoC 6. Finally, let's measure the actual voltages, and look, they're nearly the same as well. What happens if you have a noisy power supply? Well, this whole thing is dependent on the measurement of the reference resistor and the thermistor being taken at exactly the same supply voltage. If the current changes because of the power supply noise, you'll end up with a less accurate reading. The averaging that we're doing in the ADC helps to filter out the noise, but I'd like to change it so the system is not referenced to the external analog supply. Let me show you how you can do this by using the internal reference of the chip and an OpAmp to improve the overall measurements. First, copy the project and then paste it back into the same workspace. Now rename it to 26 ADC OpAmp VREF. Change A0 back to just an analog pin. Fix the external component wire, and then inside of the chip, there's a very accurate, very stable analog reference called VREF. In fact, this is also the signal that the SAR uses to get accurate measurements. But you can access this signal in your design. To do that, add the VREF signal to your schematic. The VREF voltage can be selected in the system settings in the design-wide resources if you want something other than the default value of 1.2. But that 1.2 is perfect for what we need, so we'll leave it at that. To get the VREF signal to an output pin, first I'll buffer it with an OpAmp. Change the settings and make it a follower, also known as an analog buffer, and change it to output to a pin. Then wire the output of the follower to A0. This time, we know that the maximum voltage across the thermistor or the resistor will be much less than 1.2 volts. So we can change the ADC VREF setting to be the system band gap, which will give us a measurement that is more immune to power supply noise. Now we need to start up the OpAmp in the main_cm4.c. All right, hit program. When I look at the terminal program, I can see that I get input voltages of around 0.6 volts at room temperature, which is exactly what we expected. All right, I've shown you how to use the analog to digital converter, the built-in OpAmp, so we got some more good stuff coming, so keep paying attention. As always, you can post your comments and questions in our PSoC 6 community, or you're welcome to email me at alan_hawse@cypress.com or tweet me at AskIoTExpert. Thank you.